Okay, let's start off the next session of the afternoon on domain acquisition. And Peter's going to talk about domain model acquisition in domains with action costs. So there's a sort of work coming from the Lockham area, a nice piece of work, and coming from object-centered representations. So take it away.
Yeah, I've got my own, thanks. Okay, so hi everyone. I've moved from Teesside Uni to Schlumberger in the period between this paper being accepted and me presenting now. But my co-author Alan is still at Teesside, so the paper is about domain model acquisition, and there's been quite a bit of activity in this area at ICAPS, but I'll try and motivate some of the area to get people excited in the general field and say why we're looking at these problems in the longer term. Okay, so domain model acquisition is all about modeling, and so we can see from a simple observation why we would need some of this technology. Okay, so modeling is inherently difficult, right? But it's not only on the catwalk that we can see this, and it's not only in planning. So this is from a book on document engineering. And the first sentence in this section is, modeling is inherently difficult. And the reason that they give in this nice box is there's no single way to create document and process models, right? And you can see that exactly the same in the planning community. There's no one domain model that represents whatever it is that you're trying to work. And so, you know, one alternative way of seeing this is that you've got somebody who's a domain expert who wants their domain modeled, right? And they found out this little bit about planning modeling, okay? So they know a little bit about planning and lots about the domain. And there's a modeling expert who knows lots about modeling and nothing about the domain, okay? So he comes and asks for advice, and well, you need to talk to the expert, and you find out a little bit about the domain. You write something, and then the modeling or the domain expert says, that doesn't represent my problem at all. It doesn't count this problem, that problem, the other problem. There's lots of constraints that aren't in there. Okay, so you go away, you read a book, and you learn a little bit more. So as the modeling expert, you're learning more and more about the domain. The domain expert might not even be a technical person, right? So they may be a curator of a museum or anything, and they might have no way of becoming this modeling expert. So their modeling knowledge isn't growing, but your domain knowledge is growing. So you learn a little bit more, and now maybe you're at the stage where you've created a reasonable domain model for your domain expert. Well, there might be some other corner case that you haven't taken into account. And at this stage, your brain is a bit full, okay? So, like, we can't fit any more domain knowledge whilst retaining all the modeling knowledge we already had. And so, we need some better way of modeling these things other than relying on people with PhDs in planning. Okay, so let's see another way of looking at this. We all know that there's some relationship between model complexity and difficulty of solving problems, right? So we know there's no linear axis of model complexity, but we know roughly as model complexity increases, then our solving difficulty increases too. Okay, so let's imagine we've got this complexity requirement for our problem, but also we've got this solving budget. Okay, so we're coming in way too high on the requirement, right? So one way of solving this problem is to remodel our problem at some kind of lower complexity. But that isn't always realistic. Sometimes you remodel at a lower complexity and you simply now are solving a simplification that's too simple. Okay, so we're going to throw away that idea, and so we're going to go to the planning community and say, well, what can you guys do? One of the things you can do is provide some algorithmic improvements, right? So, for example, we've got some state-dependent action costs, and as one of the talks this morning, the classical planning section presented, well, now we've made some algorithmic improvement, and we can now incorporate state-dependent action constant heuristics, and we can solve more problems in that space. Okay? But also, another thing that we can do is model these things better. Okay? So there's more than one variable, right? The algorithm's variable, we can improve that, but we can also improve our model in order to solve problems whilst retaining the same complexity. And then, abracadabra, we relay our requirements for both things in there, and we have our solution, right? So all we have to do is pull this line down. Okay, so it's in this better modelling space that domain model acquisition systems are going to live. That's what we're trying to help. So there's a few ways we can help, and on the right-hand side, we've got this idea of reformulating existing models. And this morning we saw some examples of this. So we saw these polynomial reductions that we can do in order to transform one model automatically into another model. But importantly, that requires somebody to have created a model in the first place. Okay? So we can do macro actions, there's entanglements, there's all sorts of different reformulations that you can apply to your model, which enables you to solve that more simply, right? We're just pulling that curve down, okay? On the other side, we could help an inexpert domain modeler to domain models more easily, okay? So we can provide tool support, so things like It's Simple and GPO. We can teach people, right? I mean, education's probably quite important. I mean, we teach people to program in Java, we teach people to program in PDDL, that's probably going to help. But the topic of this talk is in the automated modeling tools. So this is how do we go from some description, so something from the real world, straight to a PDDL model. Okay? Okay, so a lot of these systems are based on the ideas of inductive reasoning. Okay, so in inductive reasoning, we have some inputs to our system. We've got a set of positive examples. So this is kind of solution-guided reasoning. So set of examples are usually plans. So here's a set of plans. A set of negative examples. So here's a set of things that are not plans. And a collection of background information. And that could be anything. And our output is some kind of domain model consistent with all of our inputs. Okay? So I said a set of negative examples, but in fact, most people doing domain model acquisition in planning are not using negative examples. So that's an interesting avenue to explore for people wanting to continue this line of research. Normally, our positive examples are a set of plan traces and some other clues, perhaps. We'll come to that later. I mean, they don't have to be plan traces. You could go straight from a natural language description of a planning domain straight into PDDL actions. That would be another way to do these things. And a collection of background information, and typically these are assumptions about the target language that we're looking at, right? So you make some assumptions that we're using strips without any conditional effects, or some of these things, and that allows you to construct solutions appropriately. And the output of the system is obviously just a domain model. Okay? So this work, which is NLOCM, which means numeric LOCM, builds on all of the kind of LOCM-based systems. And these are special because they assume that we're using a minimal amount of input to the system. Okay? So typically, we're only using plan traces and maybe one or more clues. Okay? So 2009, LOCM learned the dynamics of many domains using only plan traces. Okay? 2011, LOCM 2, this is where I started to be involved in any of these things, increases the range of LOCM to domains where objects have separable behaviors. Okay, so Lockham constructs small finite state machines to represent objects. Lockham 2 also allows objects that are represented by 2 or more finite state machines. Okay. 2013 was the first work at all on static relations in Lockham, and that was based on manual hints. So this was the KR write-up in the journal paper of the original Lockham 1 system. And then in 2015, there was LOP and also ASCOL, which learned static relations, and the LOP system relied on optimal plans. And then 2016, which is what you're seeing today, N-Lockham, numeric Lockham, we're learning domains with action costs. Okay? So I'd like to point out that the Lockham, Lockham 2, LOP and N-Lockham papers were all published in ICAPS. So like kind of I and co-authors are very grateful for the encouragement that the ICAPS community paid to this, and appreciate that people understand the importance of this kind of breadth of work. Okay, so if we're looking at the particular thing for N-Lockham, we're learning domains with action costs. Okay, so I'm going to show 2 operators that include action costs. I mean, we all understand what they are, but just to point out that this first one is a pickup action in the trucks domain, and it has a constant action cost, right? So it relies just on this value 1. The drive action depends on the road length between two of the parameters of the action. And this is a static fact in the initial state. It has to be for the action cost assumption. But just to point out that it's the location parameters that it depends on. Okay? So in domain model acquisition, we're going from plans to a domain. So we can see the plans on the left-hand side. And notice that in these plans, we've also got the final cost of the whole plan. Okay, so the extra clue that we give to N-Lockham in order to find the action costs as well as the domain structure is this final cost of the plan, because we need some kind of evidence of what the plan costs. And then how do we do this? Well, we want to derive some state machines, as I said, as it happens in Lockham, but we're going to, we're going to annotate these state machines with numbers, okay? So what we're going to do, we're going to have some kind of constraint model that we're going to solve over the plan traces, and these depend on what we call templates, okay? So each of the action costs can depend on any combination of the parameters for that action. Okay, so there could be a cost of loading things into a particular truck. There could be a cost of loading things into a particular truck at a location. There could be a cost of entering a location, which would just depend on the destination location, or there could be a cost of leaving a location, or there could be a cost over any of these subsets. Okay, so for the trucks domain, the cost is over the location from and location to, and we can see in this kind of table that we've got a 1 in our contribution column for the parameters set 2 and 3, which is the first and second location. Okay, so this means that you can see we've annotated these state machines, so pick up and drop cost 1 unit, and the location parameter, which is the thing in square brackets, has this C value, which is the cost of transitioning from one value to the next. Okay? Okay, so I'm going to describe the constraint model that we use to derive these action costs. But I just need a bit of background terminology. So the input to the system is a set of plans, pi 1 to pi p. We define C and L of a plan, and that's the input cost of the whole plan, of all the actions in the plan, and L is the length of that plan. And then for each individual plan, we say we've got pi I 1 to pi I length of the plan, right? So each plan is just a set of actions. And then we've got this curly A, which is the set of ground actions that we see in all plans, right? So the important thing is that some of those ground actions are shared between plans, okay? So we might have ground actions that are drawn from the same state spaces, okay? So this allows us to then construct constraints that link between different plans in our input sets, okay? And AO are the ground actions of a particular operator type, okay? Okay, so in order to do this, we use a constraint programming method. We've got a set of integer variables for all of our ground actions. And then we say that the sum of the ground actions in each plan must be equal to the total cost of that plan, okay? For all of the plans pi and big pi, okay? And now that would be enough to get us a consistent assignment to all of the ground actions, okay? But we don't just want to do that, we want to find the simplest way of representing those with respect to those templates that I talked about earlier, okay? So in order to do this, then we define our templates as a subset of that power set of the arguments of an operator, okay? So we can have multiple individual templates to represent the action cost of a particular operator. And then we're going to introduce two types of variables, okay? So we introduce a set of 0, 1 variables to represent whether a particular template is active for a particular operator, okay? And if it's 1, it's active. If it's 0, it's inactive. And we also introduce a set of integer variables to represent the ground value of that template cost, okay? And then we assert that the cost of the action is the sum of all of the ground costs of the individual contributing templates for that operator, okay? And then to finish off, all we say is that if the template for the operator is inactive, then that implies that the ground cost for that template is 0. Okay, so either the ground cost is 0 or the constraint is active. Okay, sure. Okay, and then we introduce some way of minimizing the complexity. So we favour shorter templates, and we search in a layered strategy, going from small templates effectively to large templates. Okay, so you need to look in the paper for more details on that. So in terms of results, so there's a large table in the paper. This can effectively be categorized into 3 sections. So things that only require strips, unit cost actions, they're found incredibly quickly. Things that only require operator costs, they're also found incredibly quickly. And things that have more complicated effects. And we have mixed results for those, but look in the paper. The majority of these we're solving perfectly. Okay? So just to look in the long term, okay, so clues versus complexity, right? So the idea is to get these Lockham systems to be able to solve with less clues, okay? So we're trying to pull this down here, and currently we're about here. So in this box, there's space for lots of different things, and we may be hearing about one of them just in a second, probabilities. Okay, and thank you very much.
Okay, we have time for a couple of questions. Could you not shout out, wait till I give you the mic, please?
I have a question on the motivation of the research. So, under what kind of situation do we know the overall cost of the plan, but we don't know the cost of each action?
I mean, an example would be where it was, I mean, say you had a battery on a robot and you couldn't monitor it in real time, but you could take the thing out and check the value, I guess. I mean, just to clarify, if you know the cost of each action, then you can split every plan into single-step actions and do the same thing. So you don't lose anything by using this approach. You can only gain something. So it's more general.
Time for one more quick question. Anybody else?
How do you evaluate the generated domains? I mean, suppose you have two different techniques. How can you say one is better than the other, considering the results?
So for the action costs, it's easy, because we can just check the action costs are correct. For the rest of it, it's more difficult. And so we do it by sight, making sure the domains are correct, because we have something to verify with. In general, it would help if we had some mechanical way of testing the equivalence of two domains. I mean, that mechanical way doesn't yet exist. I mean, I know that Lee's group in Huddersfield have done some work in it, but I don't think we're right at the correct answer, right?
Thanks very much, Peter. Give a round of applause again.
Thanks.
Thank you. Okay, so the second and final talk is from David Martinez. He's talking about learning relational stochastic domains for planning.
Hello, thank you for the introduction. So in this work, we are doing something similar. We want to obtain the domain model for planning, and for that we propose a new learner that will have as input a set of input transitions. So our input will be a set of completely observable transitions, such as this one, with a state, an action, and the state after executing this action. And we want to obtain a set of planning operators. These planning operators will model both action effects and exogenous effects. They will have uncertainty in the effects, and they will also have relational generalizations. And the idea is that they can be easily written in RDDL to be used by planners. And here is one example of a planning operator that says that this literal will change with a probability of 0.5 if these preconditions are satisfied. So in comparison with the state of the art, there are other approaches that learn relational stochastic action models, but they cannot cope with exogenous effects because they usually learn only one rule per transition. And here we also have exogenous effects. So here is an example problem that we want to solve, the closing traffic domain from the IPVC, where the robot has to move to the goal, but has to avoid the cars. So action effects are the effects that happen because of an action of the robot, in this case the move north action, and exogenous effects are effects such as the cars moving to the left every iterations or cars appear in the first column that happen no matter what the robot does. And finally there are also probabilities because cars only appear with a certain probability. So the robot will have to plan how to avoid the cars and get to the goal. Well, our approach has three main parts. First, we want to obtain relational generalizations from our input. Then we will obtain a set of planning operator candidates. And finally, we will select the best subset of these planning operator candidates. So we will start by seeing how we obtain the planning operator candidates. We will use LFIT, which stands for Learning from Interpretation Transition, that gets as an input a set of propositional transitions and outputs a set of minimal rules, which are not the minimal set of rules. A set of minimal rules are the ones that have the least number of preconditions that can explain successfully the input transitions. And for that, it uses inductive logic programming. And the output that we receive from here, for example, for the effect where cars appear, we may have several planning operators. Very general ones, like a car can appear everywhere with a 0.1 probability, or more specific ones, like a car will only appear in the first column with a 0.4 probability, and so on. And then we will have to select which are the right ones that we want. So now we have the planning operator candidates, but the problem with the FIT is that it takes a propositional input and we lose the relational generalizations of our input. So in our input, we know which objects are used in every literal, and by using them, we could generalize so that when we learn, for example, the move north action, we can generalize it to every position. And for that, we have this other module. And what we do is that for every object, we will transform the object into a symbolic variable. And as LFIT cannot model directly actions, we use a multi-value atom that we call action, and it takes as a value the action being executed. And we will have to use different combinations of symbolic variables, and so we will create many propositional transitions for every grounded input transition. And with LFIT, we will obtain rules such as this one that we can easily transform into relational planning operators. And we will have an optional action that in the case that this atom doesn't appear, there will be no action. And when there's no action, it's an exogenous effect. So now we have our planning operator candidates, and the most important part is how to select the best subset of these candidates. So as we saw, for the same effect, we may have different planning operators that model this effect, and we want to select which is the best one for our task. And to evaluate them, we use a score function, so that it takes as input a set of planning operators and the input transitions. And it is based on the score function by Pasula et al. And it has two main terms. One, the average likelihood, so that we want to maximize how well do our operators explain previous transitions, and also a regularization term to prefer general operators over specific ones. And this penalty term is based on the number of operators and preconditions in our set. Moreover, we add a new confidence term because we want to work fine when we have very few input transitions and also when we have a lot of them. So when we have very few input transitions, the confidence term will be lower and the regularization term will be larger. So we will prefer in these cases general operators because we cannot be sure about our predictions. Well, and based on this score function, we will do a heuristic search to select our best subset. So for the heuristic search, we will modify the likelihood function being used. The standard one, whenever an operator covers a transition change, it returns the probability with which it covers the change. And the heuristic likelihood function, in the case where no operator covers a transition change, we obtain the maximum likelihood of 1. And the score function, the heuristic score function, will use this heuristic likelihood function, and it's an admissible heuristic when we add new operators to this set. So when we add new operators, in the best case, they will cover a previously uncovered change with a likelihood of 1. So it's an admissible heuristic. And in our algorithm, in the search algorithm, we start with subsets containing each one of the planning operators. We calculate which has the best score and the heuristic scores. We remove the subsets with bad heuristic scores. We choose the best one and combine it with other subsets. And then we may find better combinations that we will store them and continue and calculate all the new heuristic scores. We remove the bad ones and we continue doing the same. We select the best one of the remaining ones and so on until we find our best subset of candidates. So one problem that we may have is that in complex domains there will be thousands of operator candidates, and we did several things to speed up search. One thing is to limit the number of subsets being used when doing the search. So in this case, if we limited the number of subsets, the argument would be faster, but we may not obtain the optimal solution. So we have to be careful with this parameter. We also proposed a modified heuristic that works well when we limit the number of subsets being used. And in this modified heuristic, we penalize slightly very specific subsets that depend a lot on the heuristic value of the likelihood. And also with things like separate operator candidates in groups, such as groups representing only one action, and also using a subsumption tree. So in our experiments, when comparing with the state of the art, on the left we have the, well, first, the variational distance models represents how good are the models that we learn. And on the bottom we have the number of transitions being used to learn. So in the triangle tower, there are no exogenous effects. So previous approaches, such as the Fasula et al., obtain very similar results. But in the crossing traffic domain and the elevators domain, we have exogenous effects which make our approach work much better. And here we see what happens when we limit the number of subsets being used. So if we look at the green, well, here on the right we have the execution time, and here on the left the model quality. If we look at the green and red lines, we see that when we limit a lot the number of subsets being used, the model quality is much worse, but also the learning time is much better. But using the modified heuristic that penalizes very specific operators, we can obtain also very good results, even when we limit a lot the number of subsets being used. And we get also a good execution time. And to conclude, we learn domain models for planning. We can model action effects and exogenous effects. We also can tackle uncertainty in these effects and relational generalizations. And we have proposed a new method that first transforms the input data to relational one. We use LFIT to get planning operator candidates. And finally, we do a heuristic search algorithm to select the best subset of planning operators. And that's all. Thank you very much.
Okay, we've got a few minutes for questions. So, first question. Oh.
So for wildfire and sysadmin, they have very complex transitions as opposed to the previous state. Are you familiar with those domains?
Which kind of domain?
Wildfire and sysadmin?
No, I didn't try. Well, the problem with other domains from the new IPTC competitions is that it cannot learn for all, well, universal quantifiers. So it wouldn't work with them. So I didn't try them.
Right. Because they're looking at the sum of the previous states that are on fire, right? That's one element. So it'd be lovely to learn that. Can you think of any ways to do that? Generalization, is that on the research?
Yeah, so to work with that, the thing would be to get planning operator candidates that also model this effect. So the focus would be on getting candidates that can cope with more complex domains, such as this one.
Any more questions? No? Let's thank our speaker again.